Welcome to this lecture series in group theory. In the previous lectures, we have seen the definition of a group and some elementary properties which are listed here. So there is this exponential notation. So if x is an element of a group G, then we write x squared to mean x times x, we write x cubed to mean x times x times x, and so on. And if we have negative exponents, for instance, suppose we have x to the power minus 3, then this means x inverse times x inverse times x inverse, which is to say that this is equal to x inverse to the power 3. And finally, if we have x to the power 0, then that is defined to be the identity of the group. So under those definitions, there are these very simple laws that we must know that we discussed previously. There is this cancellation property that if we have a group G and we have an equation of this sort, then you can cancel from the left and get another equation, and you can also cancel from the right. What you cannot do is, suppose you have ax equals ya, then you cannot necessarily cancel these two things. Okay. Suppose we have, so then we discussed the notion of the order of an element. So if we have a group G and an element of the group G, then there are two possibilities. Either there is a natural number n such that x to the power n is identity, in which case the order of x is defined as the smallest such natural number. The other possibility is that there is no such n, in which case we declare that the order of x is the symbol infinity. One simple exercise was given, which is that the order of an element is same as the order of its inverse. It's a very simple fact. And very importantly and interestingly, if we have any finite group, then the order of any element is finite. So in a finite group and for any element of the group, there is always some natural number which when you exponentiate the element by, you get the identity. It was a very simple argument using the pigeonhole principle, if you will. Anyway, lastly, we saw that order kind of governs when exactly an exponent produces the identity. So if d is the order of an element x, then x to the n is identity if and only if d divides n. That is what I have written here. So these things we discussed, and I'm assuming that we are familiar with them. All right, so let's proceed. Some problems for practice. And now let us get started. Right. So the topic of today's lecture is symmetric groups or permutation groups. They are synonyms. And the idea is the symmetries of a set. What was the idea behind a group? A group was supposed to be the symmetries of some object. And the simplest object in mathematics is a set. So we would like to talk about the symmetries of a set. Now, the only information in a set is its cardinality, so it is natural to define a symmetry of a set as a cardinality-preserving map. And what does that mean? It just means a bijection. So we define for any non-empty set X, sim X, this notation to be the set of all the maps from X to X, which are bijections. Okay, so that's just a set right now, it's not a group yet. And before we talk about the binary operation, let me mention that this is also written as perm x in some texts and also as s with a subscript of x. Okay, just a notation. And here is the binary operation. Composition is a binary operation on this guy. Now, what does that mean? It means that if you consider this map, which takes a function sigma and a function tau, and produces the composition of them, this is a binary operation on sim x, simply because the composition of two bijections is again a bijection, right? Composition is also a bijection on this guy, that's okay, but we are not talking about this object, we are talking about this object. Composition of two maps from x to x is a map from x to x, and composition of two bijections from x to x is a bijection from x to x. So that's that. Now we have a set equipped with a binary operation, and hence we can ask the question whether or not this thing is a group, and indeed it is. So if X is any non-empty set, then this thing is a group where this small circle is referring to the referring to the composition. The binary, this is a binary operation on SimX, which is the composition as we discussed here. So this is a group, and this is a very simple set theoretic exercise. We need to check 3 axioms. Associativity. Well, associativity holds because associativity holds in functions. So there is no question of it not holding here. Identity. Clearly, the identity map, which we will also denote as E. So the identity map is defined as the map which takes x to x for all x. This serves as the identity of this particular pair, right? And lastly, inverses. I won't say much about this except that bijections are invertible. They are precisely the maps which are invertible. So inverses also exist. Admittedly, I have not written any details here, but I'm sure you can fill them by yourself or refer to a text if you are feeling lost, but it should be immediate. Right, so we have a group on our hands. The set of all the bijections from x to x under composition is a group, and it is called the permutation group of x or the symmetric group of x. I don't know if I've written it somewhere. Let's see. If I haven't, I will explicitly write that down. Yeah, so the elements of this guy are called permutations of x. This is a very reasonable terminology because if you think of x or the elements of x as things lined up in a row, then a bijection from x to x can be thought of as permuting the order of occurrence of these elements, right? It's just changing the names. So you can think of it as shifting the positions of the things in the row. So it's a nice terminology. So the elements of this are called permutations of x, and this itself is called the permutation group of x or the symmetric group of x. Let me mention it here. This is called the permutation group of x, and also known as symmetric group of x. Synonyms. All right. Another notation, when x is the set of the first n natural numbers, then we write sim x as this or that, just two shorthands. Also note that if x is infinite, then the permutation group of x is infinite, and if x has size n, then the permutation group of x has size n factorial. So this is a simple set theoretic exercise, something that we learn in high school. Anyway, I'm sure you can figure this out. Also, let us introduce a notation. It's a very standard notation in combinatorics. If n is any positive integer, then this symbol, we make a bracket and write n. This means this particular set, the set of first n natural numbers. And it is a somewhat weird notation in my mind because brackets are usually used to denote equivalence classes of some element. But what to do? This is fairly standard in combinatorics. Okay, so this is the definition of the permutation group of any non-empty set. And now we want to look at examples. First, let us look at the simplest possible example. Well, the simplest possible example would be when x has size 1. That we won't look at because that's a triviality. Let's look at the example when x has size 2. So when x is equal to 1, 2, that is the example we are looking at. Let me write that. Right? So if x is this guy, then the symmetric group of x has size 2 because 2 factorial is 2. And these are the two elements of the symmetric group of x. E is the identity element, 1 goes to 1 and 2 goes to 2. Sigma is the flipping element. It sends 1 to 2 and 2 to 1. So those are the two elements of sim x. And we can represent this data by a diagram. So the two elements of the group are written this way. And if we left multiply by sigma, starting at the identity, if we left multiply by sigma, we will land up at sigma. And if we further left multiply by sigma, we will come back to the identity. So the identity operation can be thought of as two successive applications of sigma. And sigma is what sigma is. It takes identity to sigma and sigma to identity. So if we wanted, we could have made additional arrows like this, where this would have read E and this arrow would have also read E, but there is no need because the information is already captured here. Recall, this is something that we did for quaternions when we were giving examples of groups, right? So this is the kind of diagram that we drew. This is called the Cayley diagram of the group given a set of generators, but we haven't discussed all that terminology. All right, so I hope it's clear everything that we've done so far, and now we will look at some richer examples. So the next example to look at is S3, the symmetric group of the set X equals 1, 2, 3. Right? And we know that this has 6 elements in it. The size of S3 is 3 factorial. So it has 6 elements in it. Here I've listed out 3 of them. E is the identity element. Sigma is sort of a rotation. 1 goes to 2. 2 goes to 1. What am I writing? 2 goes to 3. And 3 goes to 1. Right? So 1, 2, 3 are, 1, 2, 3 are written in an order. So 1 goes to 2, 2 goes to 1, and 3, 2 goes to 3 and 3 goes to 1. So it is kind of rotating them cyclically once. Whatever, this is the precise definition. And what is tau? Yeah, I also don't know what is tau. I have to think about it. Maybe I should just flip 1 and 2. So 1 goes to 2 and 2 goes to 1. And then 3 has to go to 3. That is tau. Okay, so then what is tau square? Tau square is nothing but identity. Right? Because what does tau do? It sends 1 to 2. And if you again apply tau, you get 1. Because tau sends 2 to 1. So whatever, you can easily see that tau square is identity. What is sigma square? Sigma square sends 1 to 3, 2 to God knows what, 2 to 1, and 3 to 2. Just verify. This is the definition of sigma. Sigma was sort of rotating by 1 count. Sigma square will rotate by 2 count. Whatever. Sigma cube is identity. Right? So let's denote all this data so far, whatever we have discussed. So here I will write sigma square, and I can draw this arrow, and this arrow. What are we saying? You left multiply by sigma, starting with identity, you get sigma. You again left multiply by sigma, starting with sigma, you get sigma square. And if you again left multiply by sigma, starting with sigma square, you get back to identity because sigma cube is identity. Okay. What about tau? If you left multiply by tau starting at identity, you get tau. Great. And if you left multiply by tau starting at sigma, you get tau sigma, where tau sigma is something that you can figure out for yourself. So tau sigma does what? It sends 1 to what? Tau sigma of 1 is tau of sigma of 1. That's the definition of composition. Right? Now what is sigma of 1? Sigma of 1 is 2, and what is tau of 2? Tau of 2 is 1. So tau sigma of 1 is 1. What about 2? Well, tau of sigma of 2 is tau of 3, which is 3. So this is equal to 3, and 3 is now forced to go to 2. So that is tau sigma. And finally, tau sigma square. Tau sigma square sends 1 to tau sigma square of 1 is equal to tau of sigma square of 1. But sigma square of 1 is 3 and tau of 3 is 3. Right? So 1 goes to 3. 2. tau of sigma square of 2 is equal to tau of 1, which is 2. So this is equal to 2. And 3 goes to 1. Now, interestingly, or maybe not very interestingly, what you can say here is that you can kind of remove those arrows because tau square is identity. So if you apply tau starting with identity, you get tau. But if you again apply tau, you get back to identity. So we can denote here things by the dotted line. What have I done? Yeah. So all I'm trying to say is that apply tau, starting with identity, you get to tau. Again, apply tau, you come back to identity. Same thing here. You start at sigma square, you apply tau, you come here. Again, you apply tau, you come back because tau square is identity. All right, wonderful. Now what happens if you apply sigma starting with tau? So what is sigma tau is the question. We know what is tau sigma, but what is sigma tau? Sigma tau, we claim, is equal to tau sigma square. This is a claim. How do we see that this is true? Well, we can see this to be true by direct computation. So let's compute. We already know what tau sigma square is. What about sigma tau? So sigma tau of 1 is sigma of 2, which is 3. Sigma tau of 2 is sigma of 1, which is 2. And sigma tau of 3 is sigma of 3, which is 1. And that matches. 1 goes to 3, 2 goes to 2, 3 goes to 1. 1 goes to 3, 2 goes to 2, and 3 goes to 1. So they are indeed equal. So what we are seeing is if you multiply, or if you hit by sigma on the left starting with tau, what you will go to is this guy. So you're going this way, and then you again hit by sigma, you will go that way, and if you again hit by sigma, you come this way. And we have seen this diagram before when we were discussing the symmetries of an equilateral triangle, which was the example that we used to motivate the notion of a group. This is exactly the diagram that we saw. And therefore, even though it's not a very formal statement right now, it will be later, but we can say, or at least can appreciate the fact that the symmetries of an equilateral triangle are precisely the symmetries of this 3-element set. And that's very interesting. A geometric object is also, or rather the group of symmetries of a geometric object can also be seen as the group of symmetries of a symbolic object. This is in some sense a symbolic object. 1, 2, 3 are just 3 distinct symbols, right? And that's very interesting. That on one hand we have a geometric object, and to talk about its symmetries we need to be privy to the nitty-gritties of the geometric situation. But once we know that it is actually just the symmetries of a symbolic object, then we can do algebra. We can feed this to a computer and then just churn things out, right? This is the kind of thing that we also said in the introduction. Okay, so make sure that everything here is clear, that you follow everything. It's very important. These arrows here mean that you're multiplying by the left. So when you start with tau and you apply sigma, you are reaching sigma tau. It's another matter that sigma tau is same as tau sigma square. Okay, so it should be clear to the reader what is meant by this diagram. That's very important. Arrows mean multiply by left. You can use a different convention. If you like, you can write the symbol to mean multiplication by right. Then this diagram will be slightly different. Anyway, so that's S3. And yeah, so there is this another notation which is used to denote a permutation. Suppose we have sigma in S3 defined this way, as in the previous page. We can equivalently define or denote sigma like this. Instead of writing all of that, we may just write this thing, and it is capturing the same data. It is telling you what is the image of 1, what is the image of 2, and what is the image of 3. This is just an alternate notation, nothing deep about it. And let's write down everything that we did in the previous page by filling in the blanks. So the identity map is just 1 goes to 1, 2 goes to 2, and 3 goes to 3. Sigma is this guy. Sigma square is this guy. What is tau? Tau would be this. Tau sigma. Well, what is tau sigma? I'll have to check. So this is your exercise. Just fill it up. Okay. Just an alternate notation. I'm calling it the bracket notation, but this is not a standard terminology. I've called it the bracket notation because of the brackets. Okay. But there is another way of looking at a permutation which is very interesting and very useful, and also leads to some very interesting observations, which is the permutation digraph. So you can represent a permutation by making an appropriate graph. So for example, if this is our permutation, which is the 1 goes to 2, 2 goes to 3, and 3 goes to 1, we can denote that by just a picture. So it sends 1 to 2, it sends 2 to 3, and 3 to 1. So either we make this or write this whole thing down, or we just draw this nice diagram. It's capturing the same information. It is telling us what is the image of what. If I'm at 1 and I want to find the image of 1, I just follow the arrow. Wherever I land, that is the image of 1. Similarly 2, similarly 3. Okay. Suppose we have this this permutation. This is a permutation in S5, or the permutation of this particular set. That's what this permutation is. So let's draw out the diagram. 1 goes to 3, 2 goes to 5, 3 goes to 4, 4 goes to 1, and 5 goes to 2. So 2 goes to 5 and 5 goes to 2. So we will have to draw curved arrows. Maybe I'll use a different color. Okay, great. One more example. This time we have the set of first 8 integers, or first 8 natural numbers, and sigma is a permutation of that. Let's draw it out. 1 goes to 3, 2 goes to 7, 3 to 6, 4 to 5, 5 to 2. Really? 5 to 2? 6 to 1, 7 to 4, and 8 to 8. Now 8 goes to 8, we can denote it like this, but it's better to just leave it alone, and we know what that means. When some dot is left alone, we know by convention that it is fixed. It doesn't move. So instead of drawing this pesky arrow, we just leave it alone. Okay, and here also I would like to use a different color. So what are we seeing? There is this cycle, and there is this another cycle, and there is also this cycle which is kind of hidden from view. So in all the 3 situations, we are seeing that cycles come about and 2 different cycles do not interact. This is one big cycle here. Here we have this cycle and that cycle, and they do not interact in some sense, right? There is no intersection between the 2 cycles. 1, 3, and 4 are disjoint from 2 and 5. Here also 1, 3, 6 are disjoint from this particular orange cycle. It's this way. And then there is this lonely cycle which is also disjoint from everything else. So this is kind of pointing us towards a certain very general fact, which we will look at later in detail, which is the cycle decomposition of a permutation. Every permutation can be thought of as a product of cycles. We will see later. Okay, so just keep this in mind, and clearly this is a very nice visual way of looking at a permutation. All right, let's make some computations, and that will be it. So we have the 5 element set. So X is 1 up to 5. And I just want to compute the product of these 3 elements of S5. So what is the first element? The first element is 1 goes to 2, 2 goes to 1, and all other 3 are fixed. Similarly, the second one is 1 goes to 3, 3 goes to 1, all the other 3 are fixed, and so on. So there are these 3 things. We want to see what is the product. Recall, this is a function from this set to itself. So what is the image of this composite when you feed 1 to it? What is the image when you feed 2 to it, etc.? That is what we want to know. So once you feed 1 to it, it outputs 2. The first guy outputs 2. The second guy consumes 2 and does nothing to it. So it outputs 2. And the third guy takes 2 as the input and does nothing to it. So it outputs 2 also. So the output of 1 under this composite machine is 2. Right? So this leads us to 2. Now suppose we feed 2 to it. What happens? 2 goes to 1. Then 1 is fed here, it goes to 3. And then 3 is fed here, it remains undisturbed. So the answer is 3. So 2 goes to 3. What if we feed 3 to it? 3 remains undisturbed, so it's fed here. 3 goes to 1, and it's fed here. 1 goes to 4. So the answer is 4. And now what about 4? 4 remains undisturbed, it's fed here, it's undisturbed, it's fed here, and then it goes to 1. Wonderful. What about 5? Well, we already know what should happen to 5 because these 4 have already made a gang. So 5 has to be left alone, but let's compute. 5 remains undisturbed, it's sent here, it's undisturbed, it's sent here, it's undisturbed. So 5 goes to 5, and that is something that we may want, we may choose to draw by a cycle like this, but we will not. Just like in all the other pictures. Right? And this is a general phenomena which we will talk about later. It's there are these 2 cycles that are kind of getting stitched into this big cycle. We will look at that later. You can explore on your own. And here is an exercise for you. Right? Just try to product out this particular thing. Okay, so I think that's all. Yeah. So with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.